Energy profiles are a way that we can actually see the energy that's being absorbed and released in a chemical reaction, throughout a chemical reaction. So the reason I say and, absorbed and released, is all reactions will do both. They'll absorb some energy to break bonds like we talked about last time, and then they'll also release energy as they form the new bonds of the products. We just say that overall, if there was more energy absorbed than released, it's an endothermic reaction. Overall, if there was more released than absorbed, it's an exothermic reaction. But really everything does both, and an energy profile helps us see that. So I'm going to do a lot of color coding here if you want to follow along with that. But I have this example of a super generic reaction. We know that A, B, C, and D, those are our reactants. They're on the left-hand side. The right-hand side are our products. And if we look at this graph here, it's measuring energy on the y-axis. And this reaction pathway on the x-axis, you can think of it as like the course of the reaction, or over time as the reaction is happening, what does the energy look like? So at the very beginning of a reaction, right here, the beginning of any reaction, what we have are my reactants. We'd have some AB and some CD right at that spot. So if I give you a graph like this, you'd be given graphs. I could ask you, what's the relative heat of the reactants? We would look at the beginning of the graph and read the value off, and it would be 200 kilojoules. I'm not that particular if you put units here, because we don't do anything else calculation-wise with these numbers. I can also ask you what the relative heat of the products are. Well, our products are the chemicals we have at the end of the reaction. This is where the end of the reaction is. So they would have a potential energy of 50 kilojoules. Now, what's actually happening here? Why does this graph go up and then back down? Well, remember that our reactants, the A, B, C, and D, are bonded together. And so we have to break those bonds. We have to break up the AB and the CD so that we then have all these pieces that we can reform new bonds. And we talked about the fact that breaking bonds is an endothermic process, and it takes energy. So the reason this graph goes up at first, and all energy profiles will go up first, is because the first thing we do is break bonds. At the very top of this graph, what that represents, we call it the activated complex. That's right here. So it has a value of 325. But what that represents is some A, some B, some C, some D are reactants with all of their bonds broken. Then as we're going back down the graph, we are releasing energy, we're releasing energy. And that's because we are forming new bonds. So all graphs go up to break bonds, go down to form bonds. It's just a matter of relative one to the other. Overall, are we exo or endothermic? If I want you to calculate the heat of reaction from an energy profile like this, just ask yourself, what's the easiest way? We've talked about a lot of ways. What's the easiest way to calculate heat of reaction? And hopefully in your head, you know that means products minus reactants. So our products had a value of 50, and our reactants had a value of, sorry, my tools are covering it, 200. When I do 50 minus 200, I get negative 150. The fact that it's negative tells me it's exothermic, but also I can see from start to end on this graph, it's going downwards. Overall, we are releasing energy, and therefore this would be an exothermic reaction. So I can tell that just from looking at the graph, because the start to the end goes down, or from the fact that my heat of reaction from doing products minus reactants is negative. Another thing I can ask you here is for the EA, or activation energy. Some people call it the energy of activation. That's why the E and then the A. Essentially saying, if we want this reaction to actually happen, to go from reactants to products, how much energy do we need to make that happen, to activate this reaction? How much energy do we need in order to go from where the reaction starts to the activated complex, where at that point, once we're at the activated complex, we don't need to put any more energy in. All of the energy for the rest of the reaction will be for forming bonds, which is releasing energy. So activation energy is always looking at how much energy does it take to get up the hill? How much energy does it take to get up the hill? I would write that down. It's just going to be too messy if I do it. The easiest way to calculate that is to always take the top value minus the starting value. Those are not the official names. You would technically say we want to do the activated complex minus the relative heat of the reactants. But if you think about the top minus the start value, that will work every time. So we have a value of 325 at the very top, and we can subtract from that the value of the relative heat of our reactants, 200. So we'll get an activation energy of 125 kilojoules. That will always be a positive value because we're always putting energy in to go up that hill, so to speak. Okay, you'll try one like this and then we'll add a little more on.